I want to talk about ion transport because it helps us take the equilibrium description of the electrical double layer and describe it in a dynamic sense. And I want to talk about ion transport because often the end result, the engineering relevance of a microfluidic device often is related specifically to control of transport of ions. Okay. You may recall my describing this equation, and I think I non-dimensionalized this to get a Peclet number. And I described this as a passive scalar advection diffusion equation. Or maybe convection diffusion. I go back and forth. So this equation is good for defining the Peclet number. It's good for understanding passive mixing. It's good for understanding laminar flow patterning. But it really doesn't do us any good when we talk about transport of ions in the presence of electric fields. Why do you think that is? Yeah, I mean, the key thing is that the diffusion is one part of what's going on, but it's not the only thing. The key thing is that ions in an electric field aren't passive scalars anymore. They're scalars, but they're not passive. In the presence of an electric field, an ion will move relative to the fluid, which means that this equation, which has only one velocity, and that velocity is u, the velocity of the fluid, this velocity is not enough to describe the motion of the ion. So we might make an improvement on this. I might say, well, rather than describing the velocity of the fluid, I could describe the velocity of each species I. And I could say that u sub I is given by the sum of the velocity of the fluid plus anything that moves the ion relative to the fluid. And in particular, the thing that moves an ion relative to a fluid, if it's a charged ion, is going to be, I've already accounted for the diffusivity, and so there's a net flux of those species. But there is a convective difference between the velocity of the ion and the velocity of the fluid. And that difference is given by the electrophoretic mobility. So electrophoresis is the word that we use to describe the motion of an ion or particle relative to a fluid. And we typically, just as we can describe electroosmotic velocity with a mobility, we can describe electrophoresis with a mobility. And this mu sub EP is that electrophoretic mobility. So if I look at a specific ion, a sodium ion, a chloride ion, etc., and I trace its motion will be given by the velocity of the fluid plus whatever the differential velocity is, the difference between the velocity of that ion relative to that fluid. And that velocity is given by this expression. Basically says that the particle is charged. The motion of that particle induced by an electric field is proportional to that electric field, and also given by an electrophoretic mobility that is distinctive to that ion. Now, if you had to estimate what were some of the things that would affect the electrophoretic mobility of an ion, what might some of those things be? What's that? Charge. How do you think charge will affect the electrophoretic mobility? Do you think more highly charged ions will move faster or slower? So we could talk about a zeta potential. I recommend that we not talk about a zeta potential because I'll argue that in this context, a zeta potential, at least, so a zeta potential in the context of a particle might be equivalently useful as the surface potential we've been talking about. In the context of an ion, a zeta potential doesn't really have too much added use. We can use it, and people do all the time, but I don't think it adds to our physical understanding. Big ion, big charge, big Coulomb force, faster motion, slower motion. Faster motion. In fact, we'll find that all things equal, if you double the charge, the thing will move twice as fast. What is holding an ion back? If I take an ion and I apply a force to it and it starts moving relative to the fluid, what's the thing that stops it from moving? It basically feels a drag. Now, because an ion is no longer a continuum thing, if we try to describe it using strictly fluid mechanical arguments, those arguments are a little bit dodgy. It actually turns out that it's common to treat an ion as if it were a sphere, a continuum sphere, moving in a continuum medium. And if you do that to describe an equivalent radius of the particle, and then you compare that to the real radius of the particle, it's actually really close to describing that velocity correctly. But that's kind of a coincidence. There are two different errors in that end up canceling each other out. But this electrophoretic mobility, if we have higher charge, will be higher. And if the ion is smaller, will be higher. So it moves fast if we have a big force because we have a big charge. And it moves fast if the ion is small and therefore has small drag. We won't do any work in this class to try to derive what an electrophoretic mobility is. That basically is something that we'll look up. But for any ion, there is an electrophoretic mobility, which we'll denote with mu sub EP. OK, so with this, I can now go back to this equation, and I can replace the text with this. So I have said that the velocity of an ion is given by the velocity of the fluid plus an electrophoretic migration velocity. And this relation is correct. This on the other hand is totally wrong. So please make sure to note in your notes that this equation is wrong. Unfortunately, it's not so simple as just changing this u to u sub I. And I'll talk about why that is as we go forward. Anyone have any theories as to why that's wrong? Still awaiting theories as I erase the board. Because there's no gradient of the potential? I don't know if I heard you right. Well, to say that the gradient of the chemical potential is zero, I think you're making an equilibrium argument, but I'm describing a dynamic transport equation. Yeah.
Because now like this UI should be associated with that specific charge.
Mm-hmm. So I wouldn't describe it exactly the way you're describing it, but I think you're very close to the point that I'm about to make. So
that means like basically flux, right? If you write it like that.
Yeah, I mean the key thing is that the ui.grad ci that I've written there, back when we were talking about a passive scalar, that was a correct description of the divergence of the convective flux. but it's no longer a correct description of the divergence of the convective flux. And the reason is, to simplify it to u dot grad c, you have to assume that del dot u is equal to 0. That's correct for an incompressible fluid. To say that del dot ui is 0 is incorrect for an ion moving around in a fluid, or at least not necessarily correct. So let's talk about the Nernst-Planck equations. Just to sort of put things in context. We don't need to get into what all the other ones are. If I consider the different components of fluxes of species across the face of a control volume, one, I have diffusion, and Fick's law basically says that the flux density of mass species, which I'll denote with a lowercase j, is proportional to the diffusivity times the gradient of the species concentration. And so we can call this the diffusive component. The convective component of these species fluxes are given by the velocity of that species times the concentration. And this is similar to the same things that we might write for the momentum equation, where we could say that the diffusive flux is proportional to the momentum diffusivity times the gradient of the velocity, or the convective component, which would be a velocity times a velocity component. If we then want to determine what is the net inflow or outflow of these fluxes, if I want to take the net, determine the net inflow or outflow of a flux, what's the vector operation I use to determine that? The divergence. And this then is a description of the Nernst-Planck equation. Now, as I've written this, this doesn't really look too much like the Navier-Stokes equations. McCool, are you asking a question? Yeah. There definitely should be a minus sign in front of the divergence. Thank you. This doesn't really look that much like the Navier-Stokes equations or the passive scalar advection diffusion equation. Well, it depends on how you look at it. I don't think it looks very similar. And the reason is because typically when we write the Navier-Stokes equations or the passive scalar advection diffusion equation, we take this divergence of this gradient and we get a Laplacian. And so we get a diffusivity times the Laplacian of something. And then we take the divergence of this flux term, and we get two terms, one of which we make go away. Right? So if I wanted to take this equation, which basically specifically writes the fluxes and then evaluates the divergence of those to tell us how the change or how the concentration is changing, I would evaluate this term. I have the divergence of the gradient of Ci, and that becomes the Laplacian of Ci. To do that, I have to assume that this diffusivity is uniform. But if I take this part out, I get di times the Laplacian of Ci. If I evaluate this divergence of these two terms, I basically have to use a vector product rule. And I get this. So I have a diffusive term, which we saw in the passive scalar advection diffusion equation. I see a convective term, which I saw in the passive scalar advection diffusion equation, a temporal term. And the key thing I get that's extra is this business. Now, if the scalar is a passive scalar, then u sub I is equal to u of the fluid, and the divergence of an incompressible fluid is 0, and I was able to make this go away. But in general, because this ui has an extra component, and I can't assume that that component is divergence free, I need to keep all of this business. And in fact, in my experience, this version of the equation that I've written at the bottom doesn't really help us that much relative to this version. And so you'll find that this is the version that I'll use. You will find that this term ends up going away in the bulk of the fluid. But in the bulk of the fluid is the one place where you usually don't have to bother focusing on the ion transport. The place where you need to pay attention to the ion transport is in the electrical double layer, and that's the part where this term becomes non-zero. Comments, questions? If I wanted to take this Nernst-Planck equation and I wanted to apply it to the electrical double layer, and I wanted to look at transport in the y direction, and I wanted to derive the equilibrium distribution of chemical species, what simplifications could I make? Is there a term in that Nernst-Planck equation that I can eliminate if I'm solving for an equilibrium distribution? Yeah, I can make the unsteady term go to 0. And what that basically says is I have the divergence of fluxes. The divergence of the diffusive flux has to balance out the divergence of the convective flux. The diffusive flux comes from the fact that I have high ion, if I look at the counter ions, for example, if this is my surface, I have high ions here, and there's a diffusive flux away. The other term says that there's a net velocity of ions migrating towards the wall because there's an electric field driving them towards the wall. Right? So if I looked at the net fluxes of the fluid velocity, there's no fluid velocity normal to this wall, but there is a net ion velocity. Counter ions are constantly being pulled towards the wall by the electrostatic force, but then at the same time there's a net diffusion of them away because of the concentration gradient. And so if you wanted to establish the equilibrium distribution of species in an electrical double layer without making my Boltzmann equation argument, my Ci is equal to Ci infinity times e to the minus energy over RT, all you would have to do is take the Nernst-Planck equation, make the temporal side equal to 0, and then that same distribution will naturally come out of this equation.